While much of the recent interest in niacin, vitamin B3, revolves around its ability to boost NAD and stimulate sirtuin activity, niacin possesses a powerful secondary mechanism, independent of NAD synthesis, that offers profound anti-inflammatory potential. This mechanism centers around its role as a high-affinity agonist of the G-protein-coupled receptor GPR109A, also known as hydroxycarboxylic acid receptor 2, or HCR2. This receptor is expressed on immune cells, adipocytes, colonic epithelial cells, and even retinal and vascular tissues, placing niacin at a crucial interface between metabolism, inflammation, and immune regulation. In many cases, the anti-inflammatory effects mediated through GPR109A activation are entirely separate from niacin's role in NAD metabolism and deserve far greater attention for their potential in treating chronic disease. The discovery that niacin activates GPR109A at pharmacologic concentrations has transformed our understanding of how this vitamin works in tissues beyond the liver. When GPR109A is activated, a cascade of downstream effects suppresses pro-inflammatory cytokine production, inhibits NF-B signaling, and reduces leukocyte recruitment and activation. These effects occur rapidly and do not require the conversion of niacin to NAD. This means that even in conditions where the Price-Handler pathway is dysfunctional, or where NAD levels are already sufficient, niacin can still exert potent therapeutic effects. One of the most exciting areas where GPR109A signaling shows promise is in gut health. This receptor is highly expressed on colonic epithelial cells and mucosal immune cells, where it plays a vital role in maintaining intestinal barrier integrity and regulating local inflammation. Activation of GPR109A by either niacin or its microbial-derived analog, butyrate, leads to enhanced mucus secretion, reduced infiltration of pro-inflammatory macrophages, and promotion of regulatory T-cell (TREG) differentiation. These effects together create a more tolerogenic and anti-inflammatory environment in the gut, which may help in conditions like ulcerative colitis, Crohn's disease, and even colorectal cancer. Animal models have shown that mice lacking GPR109A exhibit worsened colonic inflammation and impaired epithelial repair after injury, highlighting the receptor's central role in intestinal immune balance. In the context of systemic immunity, niacin's activation of GPR109A on monocytes, macrophages, and dendritic cells leads to broad suppression of inflammatory cytokines such as IL-1S, IL-6, and TNF-A. In particular, macrophages exposed to niacin exhibit a shift from the M1 pro-inflammatory to the M2 anti-inflammatory phenotype, supporting tissue repair and resolution of chronic inflammation. These effects may be especially relevant in metabolic diseases such as type 2 diabetes and non-alcoholic fatty liver disease, NEFLD, where chronic low-grade inflammation contributes to insulin resistance and organ dysfunction. What distinguishes niacin from many anti-inflammatory drugs is its ability to simultaneously modulate metabolism and immunity. GPR109A activation in adipose tissue, for example, reduces the release of free fatty acids by inhibiting hormone-sensitive lipase, a mechanism originally thought to be merely lipid-lowering. But this reduction in circulating lipids also dampens systemic inflammation, as elevated fatty acids can activate toll-like receptors and inflammasome pathways in immune cells. This dual action, lowering lipid load and suppressing inflammatory signaling, makes niacin uniquely suited for treating metabolic syndrome and atherosclerosis. Interestingly, GPR109A is also expressed on microglia and vascular endothelial cells, suggesting that niacin could influence neuroinflammation and vascular tone directly. While this area is still being explored, early research indicates that niacin may protect against neurodegenerative diseases by modulating microglial activation states and enhancing blood-brain barrier integrity through GPR109A signaling, independent of its effects on brain NAD levels. Another underappreciated aspect of niacin's GPR109A activation is its potential synergy with the microbiome. The receptor is naturally activated by butyrate, a short-chain fatty acid produced by fermentation of dietary fiber by gut bacteria. Niacin mimics butyrate signaling, and in doing so may help compensate for dysbiosis-related deficits in SCFA production. In individuals with poor gut microbiota diversity or those on fiber-deficient diets, niacin supplementation may partially restore this critical immunometabolic signaling axis, strengthening gut barrier defenses and reducing systemic inflammatory load. In sum, niacin's role in inflammation modulation via GPR109A represents a powerful and often overlooked therapeutic dimension. These receptor-mediated effects are rapid, NAD, independent, and highly tissue-specific, especially valuable in the gut, immune system, and adipose tissue. As research continues to explore GPR109A agonists as anti-inflammatory agents, niacin remains the most accessible and biologically validated option. It acts not only as a nutrient or NAD precursor, but as an immunometabolic modulator with unique capabilities to reprogram immune responses, enhance gut resilience, and attenuate the chronic inflammation at the heart of modern disease. This distinct pharmacological identity deserves far greater clinical and scientific recognition, especially as interest grows in developing drugs that niacin already embodies.